Good morning, everyone, and thanks for joining us today. I'm Alessandro Margara, professor at Politecnico di Milano, and in this presentation, I'll talk about temporal pattern recognition in graph data structures. This work was carried out by two students, Pietro Daverio and Hassan Chaudhry, under my supervision and the supervision of Professor Rossi. Our work focuses on graph data structures and in particular on abstractions and platforms to manage graphs at scale. The title of this slide, The Future is Big Graphs, comes from a paper that appeared on the front page of Communications of the ACM earlier this year. There, a vast community of researchers advocate graphs as the unifying abstraction that leverages interconnections to represent, explore, predict, explain real-world and digital world phenomena. In fact, graphs are ubiquitous in applications, and papers from companies like Facebook and Google explain how they make a strong use of graphs to represent complex relations between users and concepts to better serve their queries. That's good, but unfortunately, managing large graphs is not a simple task. Here, we focus on two main issues. First, many algorithms to analyze graphs are really computationally expensive due to various reasons. For example, graphs are inherently sparse data structures, which make it difficult to explain data locality. This is, of course, true also in individual computers, where you may have problems with memory issues, but the problem escalates when the size of the graphs demand for distributed computing infrastructures, in which case partitioning the graph across computing nodes breaks the connections between the vertices of the graph and demands for inter-node communication. Also, most graph algorithms are iterative or recursive. Think, for example, about discovery of paths or analysis of communities or clusters. They require exploring the graph. And typically, they may require traversing, exploring large parts of the graphs. The second problem is that in most domains, graphs continuously change. They evolve over time evolution. Consider, for instance, the connections in a social network or the physical interactions in a mobile IoT scenario. This is problematic as the results derived from the expensive analysis, so refer to the first problem. Not only they are computationally expensive, but they are frequently invalidated and they need to be continuously recomputed. In this work, we focus on application scenarios that demand a rapid understanding of the temporal evolution of graphs. There are many examples. Consider, for instance, smart building and energy grids, where we may want to adjust the demand of energy with automated building management systems that optimize the use of the grid or the average satisfaction of users or the comfort of users or other metrics. Also, navigation systems where we may want to detect potential traffic jams and suggest alternative routes to optimize the traffic. Or network traffic analysis where we may want to detect anomalies that could hint a security threat, for example. So all these scenarios have something in common. They require reasoning on the structure of graphs and on events that change the shape of the graph or some information attached to the graph, so to vertices and edges over time. We tackled the two issues of computational complexity and time evolution by integrating efficient approaches for distributed graph computations and for temporal pattern analysis. Specifically, we integrate vertex-centric distributed computations with complex event recognition technologies. So let me start with vertex-centric programming. Introduced by Google Pregel almost a decade ago now, The vertex-centric programming model defines computations from the perspective of individual vertices. It is an iterative process where at each iteration, vertices can exchange messages with their neighbors, and then they change their internal state in response to the messages they have received. The computation stops when a given terminating condition is met. So in this abstraction, developers only need to specify the behavior of an individual vertex, and at runtime, the system automatically handles graph partitioning, communication, synchronization, and execution of the logic over all the vertices. Now, the second technology we consider is complex event recognition. Complex event recognition is the task of recognizing situation of interest or complex events from possibly unbounded streams of observations or primitive events. Complex events are defined starting from primitive events using some complex event specification language, which enables to predicate on the type, content, and most importantly, on the order and temporal distance of primitive events. So the idea is we want to specify situations of interest, and to do so, we must be clear about what brought to that situation, which sequence of events, sequence of primitive events brought us there. Our proposal integrates vertex-centric computations and complex event recognitions by providing a unifying language, a unifying programming model and processing platform for both. We consider a labeled graph, that is a graph where vertices and edges are labeled with information about their state. For instance, in a social graph, vertices may be users labeled with their profile data, their name, age, whatever. Then input events from the external environment may change the structure of the graph, for example, adding or removing vertices, or the information, the labels that are associated to vertices and edges. For instance, in a social graph, a user may become friend of another user. So there is an addition of an edge from one user to another one, may be labeled with the friendship relation. Or a user may update its profile data. So there is an update of the information, the label associated to a vertex. Vertex-centric algorithms may be used to derive implicit knowledge about the graph and keep it up to date. For instance, a community detection algorithm may analyze communities of users to keep them up to date as users interact. Okay, so there are changes into the graph, and there is something that is explicit, so they are the labels directly attached to the vertices, or other information may be derived using vertex-centric algorithms that prove to be efficient in existing work. Then changes to the graph that come either from external environment as well as from computations on the graphs, both of them become the input for complex event recognition. So our system enables expressing event recognition patterns that predicate on the temporal evolution of both explicit properties of the graph and properties that are derived using vertex-centric computations. As an example, one may look for a daily increase of connections to a given user, suddenly followed by the creation of new communities. This can be useful to, for example, rapidly detect trends in social media and customize content delivery accordingly. The increase in the number of connections may be determined by looking at input events, addition of new edges, whereas the evolution of communities may be derived through vertex-centric computations. So once again, we have a complex event recognition system where primitive events are both events that are directly generated from the external environment or results of computations on the graph. This approach brings some key benefits. First, we provide a unified language that enables to express temporal patterns, complex event recognition patterns that seamlessly include and predicate over the shape of the graph and the temporal evolution of the shape of the graph, as well as the temporal evolution of the result of vertex-centric computations. Second, we build a unified processing engine that can leverage the knowledge, the interconnection of the complete patterns to optimize processing and avoid unnecessary computations. Specifically, the engine may postpone complex vertex-centric computations until they are strictly necessary for our tasks, so for evaluating the occurrence of a pattern at a given point in time. In many cases, it may avoid the computation of complex vertex-centric computations entirely, in the case the pattern can be falsified by other means. This is an ongoing research. In the paper submitted to this workshop, we presented the core idea that I already highlighted in the previous slides, and we introduced a pattern definition language. You can refer to the paper if you're interested into the details. And then we formally defined the semantics of this language using logical formulas. We started to implement our ideas into a prototype, the flow graph distributed platform. Flow graph adopts a master-workers architecture. There is a master that receives information from the external environment and distributes them to relevant workers. The workers store partitions of the graph according to their available resources in terms of memory and processing power. For instance, in this figure, there is worker 1 that stores 2 partitions of the graph, P1 and P2, and worker 2 that stores 4 partitions, or maybe because it has more processing power. Workers store information about vertices and edges in an in-memory key value data store. The data store persists multiple versions of the data, thus keeping track of historical information that may be required to answer temporal patterns. The prototype is written in Java using the Akka actor framework. The workers communicate to solve complex vertex-centric computations in a fully distributed fashion. And the master is the one that orchestrates pattern detection by requesting workers to start computations, so by sending commands to worker and by querying their state. So the state of the graph at the current point in time or at previous point in time. We performed an initial evaluation of the performance of flow graph just to prove the benefits of our ideas. And we evaluated the performance of flow graph on Amazon EC2 using up to 4 instances, meaning 16 processing cores. First, we measured the absolute performance, so the overall processing time when executing vertex-centric computations, page rank in these figures. We compared our prototype with Spark GraphX, which is a mature library for big data, big graphs processing that builds on Apache Spark. As you can see in the figure on the left, Flow Graph outperforms GraphX in medium to large scenarios and provides similar performance with very large graphs, up to 10 million vertices. In the figure on the right, you can see that Flow Graph appears to scale even better when adding more processing resources with respect to GraphX. So that proves that the current Flow Graph prototype has been built in a way that makes it comparable to existing state-of-the-art graph processing systems, But most important for us are the benefits that flow graph can bring when computations are integrated in temporal patterns, because that is the goal of our research, the core idea of our abstraction. In the paper, we report a pattern that predicates both on the structure of the graph and on the results of a complex computation. Flow graph starts the computation only when strictly necessary, avoiding it most of the times. So the results shown in this slide present a reduction of the average processing time for each input event by nearly 7 times. Of course, the concrete numbers depend on the specific pattern, and much better results could be achieved with patterns that allow to skip computation even more often. So this is just a single example in which we show the benefits of integrating the knowledge of the structure and temporal evolution of the graph inside a complex event recognition engine. The complex event recognition engine can optimize processing to discard complex computations as much as possible. To conclude, we propose a unifying abstraction to reason on the temporal evolution of large-scale graph data structures and to detect temporal patterns of interest over such evolution. Our programming abstraction grounds on established technologies, vertex-centric computations, and complex event recognition. And this is implemented in a prototype system called Flow Graph. As I already mentioned, this is an ongoing research project, and we are currently exploring many research directions. First, we are extending the library of computations that our engine supports. Our engine enables developers to write their own custom computations, but we are creating a rich library to simplify the usage of the engine. Second, currently, pattern evaluation follows a static scheme, a static plan, and we are implementing pattern rewriting techniques that automatically optimize the pattern evaluation plan to always postpone and possibly skip complex graph computations based on the knowledge of the pattern. Third, we are exploring dynamic graph repartitioning strategies. This is important when the graph evolves to redistribute vertices across workers over time in such a way that the load across workers remains balanced. Finally, we are looking for real-world workloads, datasets, and queries to better evaluate the benefits of our proposal and guide the future research directions. So if you have any dataset or problem that you think can be solved by our abstraction and by our flow graph engine, please let us know. And that concludes my presentation. Thanks a lot for your attention, and I'm of course available for discussing with you, for comments, suggestions, or questions. Thanks.